Okay, so are we recording? Oh, all right. Okay, so we talked about gases mix, spontaneously mix, and when we started the discussions, we talked about gases which mix without a reaction. All right, and even then you knew that that's a spontaneous process. All right, and that's because of the change in free energy. Of course, if something is spontaneous, there must be a negative change, meaning that the system might be going to a position where the total Gibbs energy is going to be lower than what it was earlier. So the delta G is negative, right? But when two gases, when they are mixed, when they don't react, it is clear that there is no heat of reaction involved. That means enthalpy change is not there at all, right? So if there is free energy change, which is negative, and there is enthalpy change, which is zero, then there must be something which is related to the entropy, which is actually driving the reduction of free energy, right? So it turns out it is the mixing of gases and the entropy because of that, the entropy change because of that. Entropy change meaning the increase in entropy because of that, the gases spontaneously mix, which is manifested in the negative change and gives free energy. And what is the physical interpretation of that is that you have one gas confined to its own volume and there's another gas confined to its the second volume. But then when you allow those two gases to mix, that means you don't create a partition or you take the partition out, then the first gas has the total volume available to it, as well as the second gas. Second gas also has total volume available to it. So the gas particles or gas molecules have a higher or a lot bigger space to move around or to distribute themselves. And like that, the second gas also has a bigger space to distribute itself than it was before the mixing. So in that process, there is increase in the entropy, which is what is giving the mixing is a favorable process, right? Now, take that concept to a little more difficult level where you talk about two gases and they react to form another gas or more gases. Just to keep it simple, we can say that there are two gases who are reacting to form another gas. Now, that's a reaction by itself. Talk about H2 plus O2 is H2O. That's a reaction, that's a chemical reaction. And those two gases could react to form another gas or liquid. We're not talking about liquid yet. Let's talk about something where two gases form another gas. All right. Now, there is reaction involved, but at the same time, there are gases which mix within themselves and react, right? So the aspect of free energy change because of mixing and free energy change because of reaction, when those two changes in free energy are mixed, that gives you the overall change in free energy, which actually defines the process, the equilibrium of the system, and everything else. Right? If you don't consider the mixing of the gases, you say that the reaction will be favorable or not based on only the Gibbs energy of reaction. If you don't consider the reaction, only consider the mixing, then you don't talk about the energy of reaction. You only talk about the entropy change because of the mixing, and eventually that is converted into the change in Gibbs energy. But then those are independent cases. Those two have to be added together to understand what's overly happening in the system, right? Which is the two components, which is what is written here in that, if you can go back to if you want to calculate the total G free energy of the system and then find out the two components, you'll see that there is this del G part, which is the Gibbs energy change because of the reaction, and this part, okay, you can talk about this or this same thing, and this part is because of the mixing of Yeah, you're back. You guys, can you hear me?
Yes, sir.
Okay. Okay, so what we were thinking, what we're talking is those two parts, where this one is because of the reaction and this is because of the mixing of gases. And here it gets more complicated in the sense that you had initially two gases, which is A and B. I mean, going to the this generic reaction, but you initially had two gases, and then because of some A and some B reacting to form some C, now you have the problem of the mixing of three gases, right? Which is what is written here. Okay, this is because A and B are proportionately reacting. That's why those two are taken care here itself because of this two term. And then of course you have the third gas mixing here. And this 1 minus Na has to be based on the amount of C formed, because this one would come only when more and more C are formed, right? Initially when Na is, let's say, the amount of what is it? Um, A. Okay, that's amount of A that's there in the system. Um, so if it is initially you're reacting, it's completely A. Okay, it's all A, B, and there's no C. When there is no C, del G zero contribution is going to be zero. So it's about not at all about reaction. It's only about mixing, and that's where A and B would mix. That will give you the initial reduction in free energy, and subsequently when the reactant forms C, this portion is coming in. Okay, which is what is given here. Uh, so this line is only because of the enthalpy or the Gibbs energy, right? And I say to you again that enthalpy and Gibbs energy for this reaction is immaterial. You can say that it's equal because the entropy change because of the formation of the new gas is negligible. And that's because from the reaction point of view, the entropy change because of the reaction is negligible because two gases are reacting to form two moles of gases, so there is no major change in the reaction. So only the exothermicity or the endothermicity of the reaction is going to come in here, which kind of scales linearly with temperature. That's why you have this one. More and more products are forming, more and more C are forming. So depending on the proportion of C forming, the contribution of this Gibbs energy of formation part is kind of increasing. And here it is coming in the negative direction. So because the reaction that we're talking is an exothermic one, right? So this is the reaction part. Whereas this one is only the mixing part. Okay, this talks about the mixing of the gases and the free energy change because of that, not taking into account the free energy of reaction part, right? So you'd see the typical curve when you have completely A and B, that's there's no change, and when you have A and B in kind of proportional amount, uh, then you have a minimum. Well, that's where the maximization of entropy happens, and it kind of again comes back to all of C, right? When these two curves are mixed, that I'm sorry. I'm sorry, I was referring to wrong curve. Here, this is what we're talking about, the simple mixing of gases, where you start with A and B because of this, because of A and B mixing, you have this much of reduction in free energy. And there again, you have A and B and C mixing. This is where it gives you the maximization of entropy. That sort of relates to the most negative free energy. And again it comes where from as we go from here to here towards the right, you'll see that A and B are disappearing and more of C are forming. And again towards the extreme end of the reaction, you'll see that there is no A, there is no B, there is only C, right? If there is only C at the eventual terminal point, then the concept of free energy change because of mixing doesn't arise at all, because it's only one gas, right? So that's the point where it is, if it is completely C, that means when the reaction goes into completion, then you're left with only C, and therefore the uh, Gibbs energy change because of the mixing part is going to be zero, right? So this line and this line would actually add up to give you this line, which is the eventual total free energy change line. All right, and when you differentiate this one, you'll get the particular composition where it's going to be the most negative free energy that corresponds to the equilibrium, and this is what it is here, right? And this composition, equilibrium composition, is the composition for a specific temperature for this reaction, which actually takes care of the reaction part as well as the mixing part. All right, so that's what we talked about. And for this reaction where del G zero is minus 5,000 joules and temperature at 500 Kelvin, that gives you the composition that Na and Nb are 0.523. That is 52% of A are still available. That means 47.7% has proceeded. That's the reaction completion process. 47.7% the reaction is completed, and that's where the system is in uh, the most minimum free energy position, and that's where A and B and C are there in the system, and the system is in equilibrium. And then you'll have to do something to either go to the forward process or to the backward process by changing reaction parameters. That was the idea, right? So to take this discussion forward, if we can see what are the effect of two variables, pressure and temperatures are typical variables, and that can shift the reactions into different directions, right? And that, if you look at the basics of it, both the parts in the total free energy expression that we had, because of the reaction as well as the mixing part, they are dependent on the temperature. Right? If you change the temperature, the del G zero that we had taken at 5,000 joules negative could change. That was at 500 Kelvin. If you take it to 600 Kelvin, it might change, right? And likewise, the free energy change due to mixing part would also change, because you have RT Ni ln Xi, a summation of that. Isn't that's the expression for the free energy change due to mixing? And you know that there is a T term involved here, right? That means when you increase or decrease T, so the total term of this one is going to be affected as well. Because in this mixing term, if you change T, this part is also going to be affected, right? So that's why we need to understand what are the changes of temperature, and how that would that affect the stability or the equilibrium of the system. It is slightly complicated in that, if you take del of del G of del T, then you get minus del S zero, right? And if you, for the reaction, if you see that del is negative, then this is going to be positive, because negative of negative makes it positive. That would mean if you increase in the temperature, increases the Gibbs free energy of mixing, it makes it more negative. So one temperature change, that means if you increase the temperature, the mixing free energy goes more negative, right? But increase in T makes del G less negative, depending on what kind of reaction it is. So from this you cannot straight away tell what is happening as the effect of temperature. So we need to follow something else, which is what is known as the Van 't Hoff equation. I think you guys might be aware of it, but nevertheless, we'll go for it once again. If you look at the Gibbs-Helmholtz equation, we've dealt with this one earlier. So you have a del T of del G by T term, right? That gives you an expression del H by T square of the negative, right? This is the del H of the reaction, right? And you know that del H is a part in the del G expression, because del G is del H minus T del H. So it sort of takes out that part and spits out the number in only enthalpy contributions, right? So if we simplify, you know that del G0 is minus RTL and Kp, or Kp is the equilibrium constant of the reaction that you're talking. So you can write an expression like this. Instead of this, you can write del ln Kp of del T is del H by RT square. Now, if we take it slightly further and take the T part out of this expression, what you can write is del ln Kp by del of 1 by T is minus del H by R. And this part is mostly independent of temperature. Why do I say mostly independent of temperature? Because you know that deep down del H is actually del H is comprised of Cp term, all right? And you know that Cp is not completely independent of temperature. Cp has slight dependence on temperatures, right? And that's why you know that Cp is A plus Bt plus Ct to the minus 2, and that kind of expression you have. But then for all practical purposes, while we are operating at normal temperature and above, you'll see that the change in temperature or change in specific heat with the change in T is not really enormous. It's only in a small band. When we go for higher resolution measurements, then we go to take care of that, or else I think we can assume that del H to be independent of temperature, and that's why for this you have a term on the right that is independent of temperature. From this expression, which is the Van 't Hoff equation, we can actually assess as to what the effect of temperature going to be on the reaction process and reaction equilibrium. Right. So let's look at this. There's two cases. If del H positive and del H is negative, these are the two clearly definable numbers for any particular equation reaction. So for endothermic reactions, where del H is positive, right, and you know that this term is going to be positive of negative. That's a negative term, right? That means what will happen is if you increase the temperature, right? If they increase the temperature, and this is reciprocal here, then, and since this is negative, Kp would also increase. Right? This is slightly complicated. Actually, not so complicated, but then you got to keep your mind still and sort of see what's happening. This is endothermic reaction that we're considering, that means this is positive, and that makes the whole term negative, right? So if you increase the temperature, that means we're actually decreasing this denominator. So increase of temperature should increase the Kp. That means the total term is again negative. Right? So increase in temperature increases the Kp, and if Kp is increased, that means forward reaction is favored. More product to form. That would mean for an endothermic reaction, increase in temperature would push the reaction towards the right, towards the product side. And it's completely negative for del H, that is exothermic reaction. Del H is negative, the total term becomes positive. And then if we increase the temperature, then Kp, the equilibrium constant, is going to decrease. So the reaction is going to be pushed to the left, towards the backside. Right? And you can actually look at some practical examples and try and apply these principles and see for yourself that if it is working or not. Likewise, you can talk about the effect of pressure on the reaction equilibrium, and in particular the reaction the equilibrium constant, right? And you know that increase in P at the equilibrium, that would shift in a direction which involves decrease in volume. And the vice versa is here, decrease in the pressure exerted on the system. If we do that at the equilibrium, then the equilibrium shifts the direction which involves increase in volume, right? So a basic approach to understand this is, let's say PV is constant, right? PV is constant. So increase in P would always decrease the volume. Okay, and it's presented in a slightly different way in Le principle. I think you might have already known that. Here, what it says is, you know, it sort of nullifies the effect of the change you're trying to do. Right. So let's say if, for an example, if you talk about chlorine, right? Chlorine, a molecule that is converting into two chlorine atoms, right? So what information are we going to get from this expression? Can you guess whether this one is going to be an exothermic process or an endothermic process? Yeah, can anyone tell me whether it's going to be an exothermic process or an endothermic process? I'm not providing you any more information. From what is written here, can we guess whether it's going to be an exothermic process or an endothermic process? Yeah, can anyone speak up? Yeah, see, you have a molecular
Endothermic.
form. Yeah, tell me.
Endothermic.
That's an endothermic reaction. Yeah, sounds logical to me, because you have a chlorine molecule, which is a diatomic molecule, and then you're splitting up the molecule and you're making two chlorine atoms, right? So that means breaking up the molecule would require energy, and that's why it's more likely that it's going to be an endothermic process. You have to provide energy into the left part of the reaction to be able to produce the right part, right? So you're breaking up the molecule. That's why it's going to be an endothermic process. Okay. What about the pressure volume argument? Is the process going forward with an increase in volume or a decrease in volume, or the volume is not changed? Yeah, is volume changing in this process or not, or volume staying same because you're not adding anything up, nothing is going, nothing new is being created? What do you think? What happens to the volume?
Sir, it will remain same, sir.
It'll remain same. Cl2 is going to Cl. Okay. What about the molarity? How many moles are changing from this one to this? Here you have 1 mole of chlorine gas, molecular chlorine, isn't it? And you're producing 2 moles of 2 moles of chlorine atom. Or at least the numbers of moles are changing here, right? So based on that, what can you guess what the effect of temperature or um, pressure is going to be on the system? You know the answers, you can guess it. Okay, all of you think about it when you get some time. A simple example. And you can talk about other gases also. CO reacts with oxygen, forms carbon dioxide, or you can think about involving a solid also, you can think, but then let's only limit our discussions to gaseous phase only for this part. Or you can talk about nitrogen, reacting with hydrogen forming ammonia. That's a typical example that we've given in the past for understanding the effect of pressure and volume. Right. So the idea is that, Le Chatelier's principle is simple. PV is constant. Increase in the pressure is given to a system where the system goes for increase in volume, then it will push it back to the reaction side. If the reaction itself is going towards a decrease in volume, then increase in pressure would push the reaction towards forward direction, and the reverse, the vice versa. Right. So one more part that we kind of miss out always, and this will be very apparent when we do some problems in the future involving different kinds of gases, is that when you have a complex equation like this, all right, A moles of A plus B moles of B are reacting to form C moles of gas C and D moles of gas D. If you have to write an expression for the equilibrium constant, then you write as the partial pressure of C to the power C and partial pressure of D to the power D normalized by the partial pressure of A to the power A and partial pressure of B to the power B. And when you convert that to mole fractions, you'll have to take into account the P part, right, the pressure part. And this pressure is the total pressure. Right. Now, from here, from partial pressure, you have to convert to total pressure when you're making using the mole fraction part. Right. So in reactions where there is no change in the number of moles of reactants vis-a-vis products, then you'll see that pressure has no effect on that, because the number of moles in the product side minus the number of moles in the reactant side gives you 0. That makes this pressure is not so important. Okay, then you would say that the pressure Kp is Kx. No matter you define it with partial pressures or the mole fractions, it's going to be the same. But more often than not, this is not a balanced equation all the time. Sometimes might happen that 4 moles react to form 2 moles, or 2 moles react to form 3 moles, and things like that. This equation, in terms of the number of moles, is not balanced. Unlike you had an example where A plus B are giving 2C, 2 moles are reacting to give 2 moles. So that means there is no effect of that. All right. When there are dissimilar numbers, then you'll have to consider a pressure term in your application so that you cannot directly convert the partial pressures to mole fractions. Right. So these are some of the theoretical and conceptual aspects of gases reacting with each other to form products. Starting from the point where there's no product, gases simply mix. So you have to say the gases mix simply without a product, and gases mix forming a product, and in both the cases how and where the equilibrium is maintained, and what is the composition of the equilibrium, and how that equilibrium can be maintained with the nature of the reaction, whether it's exothermic process or an endothermic process, or a process which leads to reduction in volume or leads to increase in volume. Based on the nature of the reaction, you should be able to say whether the reaction equilibrium will be reached at which point. All right. So this kind of wraps up our discussions on gaseous phases. Then we are left with 2 more chapters. We've been rather slow, or we've been rather very elaborate on other chapters. The other 2 chapters left with is solution thermodynamics, which is a fairly important part, and how gases react with solids. And both are important for materials thermodynamics, and in particular for ceramics or metallurgies. So we'll do that with some length, right? So what I'm going to do is create a test for maybe Thursday or Friday. I'll let you know, and after that we'll again convene with solution thermodynamics post the Shiva. All right. If there are questions, I'll will try to uh, answer that. And let me stop the recording here.